Today's topic is solution of ordinary differential equation, and we discuss about here Euler's method. The general form of ordinary differential equation is dy by dx is equals to function f of xy, where y0 is equals to y of x0, in which f of xy is a continuous function of x and y in some domain D, and x0 y0 is the given point in D, and the condition y0 is equals to y of x0 or f of x0 is the initial condition. Okay, and the sufficient condition for the existence and uniqueness of the solution of, say it is equation 1, solution of equation 1 are the well-known Lipschitz condition, which is given by number 1 is f of xy is defined and continuous in D, and the region containing x0 and y0, and the second condition is there exists a constant L such that modulus of f of xy1 minus f of xy2, which is less than is equals to L into modulus of y1 minus y2 for all of xy1 and xy2 belongs to D. We now proceed the numerical techniques for solving of the equation 1 by the sequence of points xi is equals to x0 plus I into h, which is called mesh point, when h is the step length and yi is equals to f of xi or y of xi, what can be written as. Okay, now we starting here with Euler's method. Here we determine the function. In this single step method, we determine the function here phi of x, y and h of x, y, and h is the step length depending on function of x, y and its derivatives, such that y of x plus h is equals to yx plus h into function of x, y, h plus order of h to the power p plus 1 where p is a positive integer called the order of the method. Okay. Now, if we find the expansion of y of x plus h by Taylor's method, this is y of x plus h is equals to y of x plus h into y dash x plus h square by factorial 2 into y double dash x plus dot 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 h to the power p by factorial p into y of p to the power x, y to the power p x plus h to the power of p plus 1 by factorial of p plus 1 into y to the power of p plus 1 x plus theta into h, where 0 less than theta less than 1. Now, if we put p is equals to 1, then put here p is equals to 1, then y of x plus h is equals to yx plus h into y dash x plus h square by factorial 2 into y double dash of x plus theta into h, where 0 less than theta less than 1. So, if we compare it with that y of x plus h, so phi of x h, sorry, x y h, this is equals to y dash x, or is equals to f of x y. Now, if we let yn is equals to y of xn and y of n plus 1 is equals to y of xn plus 1, that is equals to y of xn plus h, where n is equals to 1 2 dot dot dot. So, then neglecting the last term and putting x equal to xn, we get y of n plus 1 is equals to yn plus h into f dash of y dash of xn. So this is yn plus if we put here xn, x equal to xn, that means y of xn plus h. Y of xn plus h means y of n plus 1. So it's given yn of n plus 1. And this is y of xn is equals to yn plus h into y dash of xn. So this will get, that means yn is equals to h into f of xn yn. Thus, we get the solution yn plus 1 is equals to yn plus h into f of xn yn, where n is equals to 0, 1, 2, dot, dot, dot. This is the general recursion formula. This is the general recursion formula of Euler's method, which is a single step method of order 1. Of order 1. And the truncation error of Euler's method is h square by 2 y double dash of xn plus theta into h, where 0 less than theta less than 1 and n is equals to 1 2 dot dot dot. Okay, and if we find here the geometrical representation also, delta y is equals to y1 minus y0, it is y1 and it is y0, x equal to h, x equals to x0, x equals to x1, and y is equals to f of x. This is the curve. Now if we let y is equals to f of x be the solution of 1 and its graph is shown in the figure, shown in the above figure. Since a very small portion of a smooth curve can be thought of as a line segment, so we can write delta y by delta x is equals to tan theta, and from the adjacent figure delta y is equals to dy dx at p into delta x, and y1 is equals to y0 plus delta into y, as y1 is equals to y0 plus dy by dx at p into delta x. So y1 is equals to y0 plus h into f of x0 y0, which is the approximate value of y. This is the approximate value of y at x equals to x1, and on the same line we find the approximate value, and we find here the next approximate value also, that is x equals to x2, which is given by y2 is equals to y1 plus f of h into f of x1 y1. Thus in general yn plus 1 is equals to yn plus h into f of xn yn, and here there is a disadvantage also. If h is very small, not small enough, then the method is the method has no, there is an error, okay, and method become very slow. If h is very small, then the method becomes very slow, okay. So by using this method we can solve a differential equation. Say given dy by dx is equals to y minus x by y plus x with initial condition y is equals to 1 at x equals to 0, and find y for x equals to 0.1 by Euler's method, correct up to 4 decimal places, taking step length h is equals to 0.02. Here f of xy is equals to y minus x by y plus x, where x0 is equals to 0 and y0 is equals to 1 and h is equals to 0.02, which are given here. Now from the formula we know that yn plus 1 is equals to yn plus h into f of xn yn. So if we put here the initial value, that is n is equals to 0, that means y1 is equals to y0 plus h into f of x0 y0. As y0 is 1 here, so it is 1 plus 0.02 into f of x0 y0, that is 0 1. So 1 plus 0.02 into 1 minus 0 by 1 plus 0, that is equals to 1.02. So y of 0.02 is equals to 1.02. Next, if we find y of 0.04, that is equals to y2, this equal to y1 plus h into f of x1 y1, that is 1.02 plus 0.02 into f of x1 is here 0.02 and y1 is 1.02, that is 1.02 plus 0.02 into 1.02 minus 0.02 by 1.02 plus 0.02. So by calculating we get here 1.039231. Similarly, y of 0.06, this is equals to 1.039231 plus 0.02 into 1.039231 minus 0.04 by 1.039231 plus 0.04, that is equals to 1.057748, and y of 0.08, this is equals to 1.057748 plus 0.02 into 1.057748 minus 0.06 by 1.057748 plus 0.06, that is equals to 1.075601. And finally y of 0.10, that is equals to 5601 plus 0.02, 1.075601 minus 0.08 by 601 plus 0.08, and we get 1.092832. So y of 0.1, this value is equals to 1.0928, correct up to 4 decimal places.